right. Thank everyone for being here. For everyone that is officially enrolled in the course, I want to give you the official welcome for the first lecture for the Physics Without Frontiers Quantum Machine Learning course. I'm really excited and thrilled to be able to teach a little bit about some of the work that we've been doing and that I love so much about quantum machine learning and the state of the art about near-term quantum computing. For people that are watching in YouTube, I hope that this is also an enjoyable experience. And let me just first tell you a little bit what the course is going to be about. So the main idea of these lectures is to provide an introduction to the basics of quantum machine learning. So we're going to start with a presentation that I've made to give like a brief introduction, like a bird's eye view about what quantum computing is in the near term. Variational quantum algorithms, quantum machine learning, those might be terms that you probably have heard from Amira's talk and that we're going to be repeating and trying to understand in detail. And after that, this is the only part of the lectures that is going to be in presentation. From here onwards, most of it is going to be in Blackboard. So I hope that this is an enjoyable experience for everyone. If you have any questions, please just, for people that are on the call, just unmute yourself. Feel free to interrupt me. The more questions you ask, the more we make this a back and forth between me and what you're particularly interested in. I think that's going to be better. So first of all, let me give you a little bit of context about myself. So I'm originally from Guatemala. I was born there and I lived my first 18 years of life there. I then traveled to Argentina, where I studied my undergrad and my PhD in the University of La Plata, which is a small city 50 kilometers south of Buenos Aires. I was working in condensed matter, quantum information, and generally foundations of quantum mechanics. So 3 years ago, I traveled here to the United States, to New Mexico, to Los Álamos National Laboratory, where I've been working in near-term quantum computing. And ever since, I've become a staff scientist at the Information Science Division here at Los Álamos National Laboratory, where I've been working in the general theory of quantum machine learning. So this is a little bit about myself to give you a context about my background, where I've been, what I've been working on, and what are my particular interests. So this is an outline of this first lecture. I'm going to try to just take you through some of the notions that we're going to be going into more detail once we go into the proper Blackboard lectures. But here I just want to give like a bird's eye overview of why do we care about quantum computing? What is the promise of quantum computing? What can we expect for quantum computing in the near term? And more importantly, what is this buzzword quantum machine learning that you might have heard? I mean, probably you've heard because you're enrolled in this course. So let's get started with this. So of course, we all know that classical computers and the idea of classical computers is actually quite old. It started in the 19th century with Charles Babbage's studies on mechanical computers. And the evolution of modern computers has seen a series of changes from one type of physical realization to another. You know, the first programmable digital quantum computer was created in 1943. It was called the Colossus. It took an entire room for it to work. And from there onwards, we've had this very rapid and extremely potent development of computers. And this has been seen and sort of coined with Moore's law that tells us that the number of integrated circuits, or the power of the integrated circuits, should double every year with this sort of like exponential growth. And for quite a while, Moore's law has been standing, and we've seen a very rapid development of the power of classical computers. But of course, like everything that is good, it has to come to an end. And you know, there's been talk about the end of Moore's law, and specifically in 2019, the CEO of NVIDIA said that Moore's law is no longer possible. So you know, why do we say this? Because the main idea of what people have been trying to do with classical processors is that we've been developing transistors and microchips. And what we've been trying to do is pack the largest possible amount of them in the smallest possible volume. So that means that, as you can see in this plot, the size of the transistors have been just decreasing and decreasing over the years. And of course, the issue that we encounter here is that there comes a point where our devices are so small that quantum effects start to play a role. You start to see the effect of quantum mechanics start to play in and kick in. And this is usually, and a little bit counterintuitively, but detrimental for information processing tasks. Because if you have an electrical current through a microchip and you have electrons in that electrical current, you sort of don't want those electrons to tunnel and appear in some other part of the transistor, right? So the effects of quantum mechanics, whenever your transistors are too small, can actually be detrimental. So what has been going on lately is that we're not making smaller and smaller transistors. We're making them just run in parallel and trying to pack more of them so that they work one next to the other. But of course, this means that Moore's law has sort of already gotten to a limit or is starting to plateau. And the question is, of course, how do we go about trying to go past this plateauing of Moore's law? So we can think about multiple options about how to circumvent those quantum mechanical effects. So one of them is maybe we can develop a new type of microchips where the quantum mechanical effects are tamed, but this seems extremely difficult. Or maybe we can also think about an alternative approach where this set of rules of quantum mechanics that seem to be detrimental for information processing tasks at a very small scale, we use those to our favor in this new paradigm of using the laws of quantum mechanics for information processing tasks. And this is sort of like the idea and the inception of quantum mechanics, because we can ask the question, why do we ever want to use quantum mechanics for information processing tasks? And as we know here, the problem is that there are certain tasks, and we can think about some of those in scientific research, that require an extremely large processing power. So, for instance, studying the very phenomenon that hinders small transistors, which is quantum mechanical systems, it's a very expensive computational task. And this is due to the fact that in quantum mechanics, as some and probably all of you know, we have to study the Schrodinger's equation, which is going to dictate how our system evolves under a set of interactions. And here in this equation, we have this term right here, which is the Hamiltonian, that as we know, it contains information about the interactions of the model. So we have a quantum system, and this term right here, the Hamiltonian, is going to describe the interaction. It's going to have a term about, for instance, the kinetic and the potential energy. It's going to have the interactions between electrons in a molecule, between the nuclei and electrons, and the nuclei-nuclei interactions. And we have to sort of try to solve this. So the question is, it's a relatively simple looking equation, but of course, solving it requires a lot of computational resources. And we can think about a very specific example. Think about, we want to try to model the structure of an everyday drug that almost everyone knows, which is the penicillin molecule. So you take the penicillin molecule, you can decompose it. It has carbon, hydrogen, nitrogen, oxygen, and sulfur. And this is how many orbitals and how many atoms the penicillin molecule has. So in total, this means that we just count everything up. We have 121 orbitals. And this is all really good, but we also have to take into account that we have the possibility of the electrons have a spin, and the spin can be up or down. So we have to also take into account the possibility that in each orbital, the electron can have a different configuration with spin up or down. So that means that we have 242 spin orbitals that are going to play a role in this term right here. So, of course, we all know that quantum mechanics, we have to study Hilbert spaces, and the dimension of those Hilbert spaces grows with the number of constituents that we have to study. So for this particular case, we want to try to solve this equation. This is a differential equation. You can think about this as a purely mathematical problem where there's a matrix, this is a vector. And for the case that we have, this is a vector that is going to be of the size 2 to the n, where n is number of spin orbitals that we have to solve. And for the case of the penicillin molecule, we have 242 spin orbitals. And that means that to encode the state of the wave function of this molecule, we're going to need about 10 to the 75 bits of information, which is already of the order of atoms in the observable universe. So just trying to analyze a molecule like this is going to be extremely, extremely expensive. We would have to take all of those atoms, try to encode 1 bit of information into every single one of them. And of course, this is completely unfeasible, right? So quantum mechanics, as we know, it's a very large space, and trying to simulate classically the interactions and trying to study the full wave function of a quantum mechanical system is computationally extremely expensive. So this is not something that we can tractably do. So the basic idea of quantum computers was born in 1980 when physicist Paul Benioff proposed a quantum mechanical model of the Turing machine. For people that are more of the quantum computational geeky side, you know what a Turing machine is. If not, don't worry too much about it. It's a computational model about what are the algorithmic processes that we can do. And in 1980s, it was Richard Feynman and Yuri Manin that proposed using a quantum computer to simulate quantum systems. And there is this extremely famous quote by Richard Feynman, as we know, super smart guy, that says, "Nature isn't classical, damn it. And if you want to make a simulation of nature, you better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy." So the idea that Feynman and Yuri Manin had was extremely simple and beautiful. Just instead of simulating your quantum system with classical computer, just embed your simulation into another quantum mechanical system that you're going to use as a generalized Turing machine, as a quantum Turing machine, where you're going to be able to run algorithms to simulate that quantum system that is of interest. So of course, here the idea is we want to build a quantum system that can simulate quantum systems in it, you know. And for instance, if we want to go back to that penicillin molecule, if we have a quantum computer with 242 qubits, one could potentially think about simulating this molecule because the dimension of the Hilbert space with only 242 qubits is already of the appropriate size that we want. So here we use the fact that the states where those only 242 qubits live grows exponentially. The dimension of their Hilbert space is going to grow exponentially with the number of qubits. And of course, as Feynman said, this is very simple. It's a very beautiful idea. But of course, it's not easy. And specifically in the near term, it poses a significant technological challenge because up to this point, people have been working on quantum mechanics ever since the start of the 19th century, when it was shown that a new physical paradigm had to be developed to understand small systems, and that was quantum mechanics. And people usually had control over quantum systems in the bulk. So you had quantum systems that you could control. You control a bunch of particles, you control a bunch of atoms. But now we have to think about not being able to potentially control a bunch of atoms in quantum systems, but we want to control single quantum systems. So what this means is that we want to be able to individually control qubits and individually coherently act in them so that they will be able to do what we want them to do. And for instance, we can have them simulate a penicillin molecule. And that's the main idea of basic quantum computing. Of course, we can think about what else can we do with quantum computers. So we have already this original intuition that we can simulate quantum systems more efficiently in a quantum computer. And I'm going to go back to this word efficient because this is at the key and heart of quantum computers. We want to have them solve a task that is going to be faster and use less resources than classical computers. So we're going to get back into efficiency in a bit. But what other forms of information processing tasks do we get with quantum computers? So first of all, we get the possibility of performing quantum communications and information transmission. And what this means is that we can do stuff like quantum teleportation algorithms, where we take a quantum state and we teleport the state of a quantum system from one place to another without physically sending the quantum system in itself. And this is a new form of communication and information transmission that is allowed by the laws of quantum mechanics, and in particular by entanglement, which allows us to do a lot of things. And it's a key resource in quantum computing. We can also do other things like super dense coding. And we can prove that a single qubit can encode 2 bits of information. And we can use this to send information where in a single qubit, we pack more than what we would be able to do with just a classical bit of information. For instance, we can also think about encrypting data based on the laws of quantum mechanics. And these are just a bunch of things that people have thought for quantum computing and quantum information processing tasks. But for us and for the rest of this course, we're going to be more interested in the idea of quantum algorithms and what we can actually do to process information in the form of an algorithm. So, let's go back to that idea of efficiency, and let's talk about what it means to have an algorithmic complexity, and why do we have to be careful whenever we're trying to compare quantum with classical algorithms. So first, let's give a very brief and extremely simple definition of an algorithm as a set of rules or steps that need to be followed in order to solve some problem. And of course, the algorithm can be either classical or quantum. So the question that we need to ask whenever we're working with quantum computer is, given a problem or a task, can we come up with a quantum version of an algorithm that will outperform its classical counterpart? And at this point, quantum algorithm just means, we use a quantum computer somehow. Let's not worry about the details of what the quantum computer is doing right now. We're just thinking about we use a quantum computer. So here, we need to first try to understand what outperform means. How can we know that the quantum algorithm is going to outperform the its classical counterpart? And for this, we need to think about the computational complexity that is associated with every algorithm. So what we know is that every algorithm can be associated with either the runtime, how many seconds in a clock it's going to be running before you solve the task, or how many operations it needs to run before it gets to the solution. And every algorithm has this sort of computational complexity. To give you an example, let's think about taking two matrices, A and B, which are D times D dimensional, where D is just some number, and we just want to compute a third matrix, C, that is obtained by multiplying A and B. So we just want to fully characterize C in the way that we want to find its matrix elements. And we want to come up with an algorithm to do this, right? So there are many algorithms to do this. Here I just put one of them. The input can be given two matrices. We want to obtain a new matrix C that is obtained at the matrix multiplication. And we just use this formula right here. We just use a for loop where for the indexes I and J, we just literally add the product of the matrix elements of A. And we can already start to see that those for loops range from 1 to D, and we have to do this again from 1 to D. So this gives us a computational complexity of multiplying all of those runtimes of the cube. So what we know is that in order to run the algorithm for general matrix multiplication, is going to use a number of operations that scales as the dimension of the matrix to the cube, right? And this is the main idea. This is what we need to talk about computational complexity whenever we do matrix multiplication. So, of course, we can also think about, well, what about if we have some quantum system, right? What would be a computational complexity of trying to do, for instance, we want to compute the expectation value classically of matrices that look like this. So assume that somehow we managed to store those state vectors. At the end of the day, we still want to do something like compute expectation values. So we can do all of the previous steps. We have matrices here. And what we know is that the computational complexity of doing this matrix multiplication classically for quantum computers is going to scale exponentially with the number of qubits. So, this is how we can start to understand what it is that we mean that whenever we want to run a classical algorithm for some task that is intrinsically quantum, like computing expectation values, is going to have a computational complexity, right? And generally speaking, what we want and what we're going to see is that classical algorithms for quantum systems are going to typically have this sort of scaling. They're going to scale exponentially with the number of qubits that represents my quantum system. This is the typical scaling that we get for classical algorithms for quantum systems. There might be some other cases where we can try to reduce this, try to get some polynomial scaling for some specific and very special cases. For instance, if this state admits an efficient matrix product state representation, we can probably do this polynomially. But we're talking about general quantum states. We're not thinking about particular cases here. We're thinking about the general computational complexity. So, of course, as we said, classical algorithms for certain tasks have a computational complexity that scales with the problem size. So again, here, let's go back and let's think about the size of the matrix D. D here is 2 to the n. It's a dimension of the Hilbert space. Just think about D as 2 to the n. So D is exponentially with n. And classical algorithms, we are going to write this as they have a complexity that is order poly D. And this is a notation that is going to be key for studying quantum complexity and trying to understand quantum algorithms. And this is what we call the big O notation. And it's going to give us an idea about how the complexity grows. So very quickly, I'm gonna just pause here for a second and ask, just you can feel free to unmute yourselves. Are you familiar with the big O notation? How familiar are people with this sort of like notation that I'm showing here, that you might have seen it somewhere? Maybe you know it, maybe you've never known it. So I'm going to take a sip of water. I'm going to let attendees of the course just answer that question. Oh, come on.
Can you hear me?
Yes, I can.
Oh, yeah. Well, I think that I have seen that kind of notation before, and it represents, I mean, it's a shorthand notation where you want to just like to reduce all the maybe upcoming polynomials that might be writing in terms of that big O. So the term that it's inside will just kind of determine the degree of the polynomial that is the next one. So something like that. It's just a shorthand notation that just allow you to reduce all the other terms. So you're compressing there all the information. So for example, I don't know. Let's suppose that you have some expansion and you just want to, for example, the expansion of the exponential function, so e to the x. So you just want to write, for example, the first two terms 1 plus x, and then you just want to let all the other terms just be represented by that notation. So you just add, for example, plus o, and I don't know, I think that it's kind of an x or the next coming term that the one inside. I don't remember exactly what is the representation or what is the meaning of the value inside it, but in general, I mean, the whole term, the O, and and the term inside will just kind of compress or just tell you that there's more information that maybe you're not taking into account, or maybe you just want to let know the person that you're going to use it later, or maybe not. So for example, you can start to say that it's going to be higher terms or higher polynomials that might be represented by that.
Right,
But
right. Yeah, no, that is actually a great reply. And that's true. Whenever you do some sort of like Taylor series expansion, this big O notation might come into play. Because again, as you said, the big O notation is sort of condensing the information about a function and just giving me information about the leading order. What's the important thing that I need to know about this function? And this is going to play a key role in a lot of the things that we're going to be doing whenever we're going to be trying to analyze if a given algorithm is going to be more efficient than a classical counterpart, because that's the whole goal of quantum computing, right? We want to show that we can outperform the classical algorithm, so we have to analyze the computational complexity. And what was your name again? I don't think you mentioned that, but just so that I know.
oh yeah, I'm sorry for that. Yes, my name is Carlos.
Okay, Carlos. Perfect. Thank you very much. And as Carlos was saying, this sort of condenses information about sort of the complexity and just gives us information about the most relevant terms. So for people who are not familiar with this, let me just very briefly give a mathematical description of this. You don't have to worry too much about this. We're going to recall this later on whenever we're working on the blackboard. But essentially what we have is that imagine that we have a function f, and we say that it belongs to big O g of x. So for instance, previously we said the function, the algorithm that multiplies two matrices A and B is order d cubed. Or we can actually write that as order poly d, because d cubed is a polynomial function of d. So this poly means a polynomial function of d, right? So explicitly what this means is that this is true if there exists a positive number c and a value x naught, which again, x is the variable here, such that f of x is going to be smaller than g of x multiplied by c for all x larger than x0. I know that's a lot to unpack, but let's just see this. So here we have in red the function f of x, and in blue the function g of x. They might have some crossings, but what we say is that there comes a point, x naught, after which my function f of x is always going to be smaller than g of x, right? So that means that we can always say, the computational complexity is always going to be smaller than this g of x. So for instance, whenever we say for the matrix multiplication of the computational complexity is order poly d, what we're saying is that, we know that we have a polynomial d cubed, but now we know that d cubed is going to be smaller than, for instance, d fourth at some point. So we know that we can talk about the computational complexity in this form right here. So again, as we said, for the case of classical algorithms for quantum systems, they scale as order poly d, where d is the dimension of the quantum system. So we can just replace d for 2 to the n. So of course, what we want to try to do now is whenever we ask the question is, given a task, can we come up with an algorithm that will outperform its classical counterpart? We know that this can be rephrased as, given a task, can we come up with a quantum algorithm that will have a more efficient scaling than classical counterpart? For instance, if we can come up with an algorithm, for instance, a classical algorithm that is a quantum algorithm that is going to scale logarithmically with the dimension instead of polynomially, that means that log d, if d is exponential, this is polynomial in the number of qubits, we are going to have an exponential speedup. So whenever we have quantum algorithms, and we can prove that their scaling is logarithmic in the Hilbert size dimension, or the same polynomial in the number of qubits, then we're going to have an exponential speedup. Or maybe we can also get a speedup that looks like this. And in this case, we're going to have just a polynomial speedup. And this is going to be at the key of quantum computing, because we don't want to have quantum algorithms that are just running maybe in the same order as classical algorithms, because then we're just using a very complex tool, which is quantum computing, to solve with the same efficiency a problem that we can already solve with classical computers. So what we want to try to do is get algorithms that will somehow fit in here. So quantum algorithms, we already know that algorithms for quantum simulations, those can be exponentially faster than classical algorithms, and they will scale polynomially with the system size. And the question is, can we come up with other algorithms? And surprisingly, and this is extremely interesting, is that we can come up with quantum algorithms that can also provide a speedup for classical tasks. Like, as we said, quantum simulation is an intrinsically quantum task. We want to simulate a quantum system. But we can also come up with quantum algorithms that can speed up tasks that have nothing to do with quantum data. Those can be purely classical algorithms. A prime example is finding prime factorings of an integer number n. So, there is a classical algorithm, which is called the number field sieve with complexity that looks like this. Let's just assume that this is what we have. And there is a quantum algorithm, which is called Shor's algorithm, developed in 1994, which is a quantum algorithm with a complexity that looks like this. So now you can see that here we have exponential of n. So this is exponentially expensive with the size of the integer. But the quantum algorithm is just polynomially expensive with the size of the number that we're trying to factor. So this is a case wherever a quantum algorithm can give us an exponential speedup over classical algorithms. And this is extremely important for cryptography, because most of the RSA encryption system that we use in internet, whenever we buy something, you put your credit card information, that gets encrypted, sent somewhere so that an eavesdropper cannot get your credit card information. This is based on the fact that finding prime factors of an integer is a really hard task. It's an exponentially expensive task. But if we have quantum algorithms, we could potentially break that, and we could potentially factor numbers very, very fast. There is, of course, other algorithms, like finding an element in an unstructured database. Imagine that you have n books, and you're trying to find one book, but they have no labels. You can just put your hand in a black bag and try to get like a book out of it. There is a classical algorithm, which is simply take a look at every element, and that has a computational complexity of order n. We essentially have to look at all of the elements until I find the one that I'm looking for. But Grover's algorithm was developed in 1995. It's a quantum algorithm with a computational complexity of O order square root of n. And this, again, gives us a polynomial speedup, because we went from linear to square root. So in this case, the speedup is not as fast as Shor's algorithm. It's not exponential, but it's still polynomial, and it's still provable. And essentially what we have here is that quantum computers, as a computational model in themselves, provide for a more powerful computational model than Turing machines or even probabilistic Turing machines. So though that's not the end of the story, there are more quantum algorithms that have probable speedups that have been developed for tasks such as performing a Fourier transform, solving linear systems of equation, performing principal component analysis, extremely important for machine learning, semi-definite programming, and there are many, many more that you can just go into this website, the quantum algorithms, who and just browse around. They're all going to tell you this big O notation about what is the classical versus the quantum complexity, and what is the speedup that you can expect from this quantum algorithm. But of course, there is one issue that in general, creating quantum algorithms is hard due to the counterintuitive nature of quantum mechanics. Because the way in which we solve a problem, usually whenever we create an algorithm, is we think about the logical steps that we need to follow to be able to get to the solution that we want. But quantum algorithms are usually a little bit harder because quantum mechanics are not intuitive, and they're extremely counterintuitive, and our brain doesn't work that way. So, just have in mind that creating quantum algorithms is usually pretty hard, and most of the algorithms that have provable scaling can be boiled down to being part of one class of problems that you can just say, oh, this is what we're doing, right? So up to this point, we have talked about the theory of quantum algorithms. But of course, to implement them, we also need experimental devices. And, for theories like myself, talking about experiments, I'm starting to get here to the bottom of my comfort zone about what is it, how do you actually develop a quantum computer? There's extremely smart people that are working in that question and that have made a lot of progress. So now let's ask the question, what do we actually need to create a quantum computer? Let's say that we already have our algorithms, right? We have them in pen and paper. There are textbook algorithms. We want to run them. We want to try to get a computational advantage. What do we actually need to create a quantum computer that is going to be able to run those quantum algorithms? So here we can think about the so-called DiVincenzo criteria that are just a sequence of requirements that you need to build a quantum computer. And this is what the experimental setup needs to meet. Those are the necessary conditions for quantum computing. So the first one is we need a scalable physical system with well-characterized qubits. So that means we need to have a way to say, this is a qubit, and this is how we build more qubits. Then we need to have the ability to initialize the state of the qubits into a simple state so that we know how the information is starting, how the state of the system is at the start of the algorithm. We can very well characterize and choose those initial states, because this is all about information processing, right? We're going to start with something. We're going to do something to it. We're going to get an output. So we have input, algorithm, output. We have to be able to characterize our input. So that means initializing the state of the qubits. We also have to have qubits that have long decoherence times. That means that we want to have qubits that are going to live enough and interact with the environment with a rate that is going to be small enough that we can run our full algorithm, get to the output, get some information out of the output before noise completely corrupts my algorithm. And then we also need to have what we call a universal set of quantum gates, which are just the operations that we're going to be using as the basis for information processing. So classical computing has their set of universal basic operations that we need to do to be able to just obtain any function on data. Quantum computing has the same, and those are going to be based on universal gates, universal set of quantum gates. And then, of course, we need to have a way to extract information out of those qubits, and that's going to be, we need to be able to have some way of measuring them and get information out of all of them. So those are the steps for quantum computing. I'm going to be mainly basing most of this talk and most of what we're going to be doing in our lectures in the circuit-based model of quantum computing. There are different models for quantum computers that are not this typical pictures that you see with the lines and the unitaries. There's other types of quantum computing. We're going to be focused on the circuit model of quantum computing. So that being said, what is a qubit? We know that we need them, but what is a qubit? So we know that in classical computing, the fundamental unit of information is the bit. And we know that a bit can take values 0s and 1. And a bit can have many physical realizations in classical computing. It can be, whenever we're using our computer, a magnetic domain where it's pointing north or it's pointing south, and then we encode a bit 0 or 1. It can be the bits in a CD. I don't know how young people are here, or if you all have used CDs for saving, your songs or whatever. But the way that this works is that you have a laser that is going to carve a pit on the CD, on the surface of the CD, or it's not going to carve a pit. So it's going to look like a lot of like pits and crevices, and that's zeros and ones, and that's how we record them, right? So those, a bit is just a mathematical concept that can have many physical realizations. And in quantum computer, it's again the same. The qubit is going to be the fundamental unit of information, and it can also take two values, 0 and 1, but more importantly, it can be in a complex linear superposition of those two states. So a qubit, again, is just a mathematical concept, and we're going to be essentially referring to a qubit as just a normalized vector, so normalized to one vector in a two-dimensional complex linear vector space that we call the Hilbert space. So just think about 2 times 2 complex matrices and 2 times 2 and 2 times 1 complex vectors. And that's just essentially what's going to represent the state of a qubit. So generally speaking, as we said, the general state of a 1 qubit state can be expressed as a linear combination of 0 and 1 states. This is the Dirac notation that we're going to be mainly using. And I'm going to go into that a little bit more later in the Blackboard talks. And what we have is that these two, A and B, are complex numbers that are normalized to 1. Why are they normalized to 1? Because the complex, the modulus of A is the probability of the qubit being on 0. The modulus of B is the probability of qubit being on 1. And we know that either the qubit is in 1 or it's on 0. And because those are probabilities, they have to add up to 1, because the qubit has to be on 0 or has to be on 1. And if we add up those two probabilities, they have to add up to 1. It's just like I say, I take a coin, I flip it, I have a given probability of tails, a given probability of heads, and those two need to add up to 1 because the coin has to land on heads or tails.
Marco, disculpa que te interrumpa. Tenemos un límite con la llamada y se va a cerrar pronto. En el chat envié el link a donde nos tenemos que conectar todos. Perdona.
Okay, so I'm being said that we need to move at some point to another link. So how long do we have? Do we know how long do we have before the school ends?
En este link tendríamos que conectarnos todos.
All right, so we'll just do like a quick pit stop now, and I'll see everyone in the new link that we have to go to.
Marco, your mic is off.
It is off. Yeah, that makes a lot of sense. Sure, whenever you're ready, just go for it. You can let me know on Slack. I have it now here open, so I'll be able to read it there. All right, so sorry about that, everyone. We had some technical difficulties, but luckily we're back here. So let me try to pick up where we last left off. So we were talking about what is a qubit. What is a qubit as a mathematical concept? So we were saying that a qubit is just going to be a normalized two-dimensional vector living in a complex linear space, which we call the Hilbert space. And we know that the coefficients associated with this linear superposition of the qubit being on 0 or in 1 can be associated with the probabilities of whenever we measure the qubit, we get a 0 or a 1. And usually it's very useful to visualize the state of a qubit using what we call the Bloch sphere, which is just a two-dimensional representation where the states that are in the North Pole are going to correspond to the 0 state, South Pole to the 1 state, and all the states of a qubit are going to be placed somewhere in this sphere. So with what we previously said about the modulus squared of those quantities being probabilities, what we have is that quantum mechanics, in a way, generalizes probability theory. And this is going to be very important in a bit. So let's just go back and say that just like a classical bit, a qubit can have many physical realizations. We can encode a qubit, for instance, in the polarization of a photon, in the spin of an electron or a nucleus, in the localization of a charge, or more generally, in any two-level quantum system. And this is what we're going to consider as a qubit. For me, and from here onward, a qubit is just a two-level quantum system, and I can be in any linear superposition of those two. So the question is, why do qubits allow for a computational advantage? Why do we care about qubits whenever we're trying to talk about computational complexity and computational advantage? So as we already said, the state of one qubit can be in a superposition of two basis states, the 0 and 1. If I have two qubits, their state can now be in a superposition of any of those four states, 0, 0, 0, 1, 1, 0, and 1, 1. And of course, if I have n qubits, their state can be in a superposition of 2 to the n states, which we denote at this set right here. And it's, of course, all the linear combinations of all of those states. So the dimension of the Hilbert space of n qubits, as we had previously said, grows exponentially with the number of qubits. And this is going to be key, because this is going to allow us to explore the exponentially large Hilbert space with a given number of qubits. So then we have to talk about, right, so we have qubits, what do we need to do with them? So this is what I was talking about, the circuit-based model of quantum computing, where I'm going to have a given set of qubits that I'm going to be able, according to the DiVincenzo criteria, to initialize in some state that I can characterize, like the old 0 state, and then I'm going to send them through a quantum circuit. So if this is the first time that you've seen something like this, this is something that we're going to use quite a lot. The way in which you read this, this quantum circuit is essentially telling us how the state of the quantum system is going to evolve. So each time that we just draw like a vertical line, this is just going to be a given time. So the circuit is read from left to right with time progressing as we go right. So here, what this means is that we have a bunch of qubits, we put them all in the 0 state, and then we send them through a unitary that is going to give us a state psi. And then we're going to perform some measurements. So each one of the horizontal lines is going to correspond to a qubit, whereas boxes that cross those horizontal lines are going to be operations that we make to those qubits. This is how we usually indicate that we're performing a measurement. So again, one of the main advantages of quantum systems living in this exponentially large Hilbert space is that quantum states can contain entanglement, and that is like quantum correlations between the data that we encode in our quantum state. And those quantum correlations have no classical counterpart, and they're actually a resource for quantum computing. So the main point of quantum computing is, first, we're going to be using the exponentially large Hilbert space. We're going to be using entanglement, but at the end of the day, it's not the fact that we are somehow just in a superposition of a very large amount of states that is going to give us the solution to a given problem. Is the fact that quantum also has the interference phenomenon, that we can use this to amplify the probability of a desired output, because people whenever you talk about quantum computing to people, they will say that, the advantage comes from the fact that you're looking at all the states at the same time, right? Because I'm in a linear superposition and I'm applying the unitary to all of them at the same time. I'm sort of like exploring the whole solution space at the same time. And this is where the advantage comes from. Well, that's not entirely true, because the problem is that once we measure, we just collapse onto one of them. And that state that we collapse to might not be the solution. So what we need is, we also need to use the interference phenomenon along with the superposition and entanglement to try to amplify the probability of a desired output. So these are sort of like the key ingredients that we're going to be working with to try to get some quantum advantage. So again, the question is, how do we realize a qubit? This physical implementation, which was the question that we were discussing, of how to actually get like a physical system to be a qubit. And the idea of quantum computers just in itself pushes the very limits of our technological capabilities. Because as we said, prior to the 1970s, we usually had bulk control over very large number of very large quantum systems, with a lot of them being a collection of individual quantum systems interacting in the bulk. And we don't have access to the individual quantum systems, we just have access to the bulk. But now we need to control them individually. And there's been a lot of development in the state-of-the-art technologies for controlling individual quantum systems. And this is what some people have called the second quantum revolution, the ability to be able to just individually control quantum systems that we call qubits, again, just quantum systems with two accessible levels. And what we see here is that, in the last couple of decades, there's been a significant improvement in the number of qubits that we're able to control and just to do quantum operations on. And this is quite rapidly growing. And this is the hope that we're going to get like a bunch of qubits. Now, of course, the question is, those quantum computers that we have, they're good. They push the limits of our quantum control technologies, but they're not perfect. And this is what we call the NISQ era, because let me just go into a little bit more detail about what it is that we call NISQ. So we already know that we have those tasks that are beyond classical computers. And we already have the promise that quantum computers can bring us this quantum advantage of exponentially faster complexity, that we can solve the problem much, much faster. But of course, the problem is that currently available quantum devices are still in their infancy. And this is what we call the noisy intermediate scale quantum NISQ era. And this is a name that you might have seen around quite a bit. And this is a name that we're actually going to use quite a bit, because this is the term that was coined to describe currently available quantum computers. And let's try to unpack this right here. First, we have intermediate scale. What does this mean? That we have a small number of qubits, usually in the order of tens of qubits, and very soon hundreds of qubits. Then they are noisy. What does this mean? That they are error prone, that the qubits are going to be interacting with their environment, because that's the thing about quantum systems. They're very prone to and very sensitive to interacting with things around them. So controlling those interactions is very difficult. And qubits are usually going to be interacting with their environments in an uncontrolled way. And this is what we call noise. We're losing information to the environment as the qubits are interacting with the environment in this uncontrolled way. And what this does is that it limits the depth of the algorithm, because again, remember, depth, how many gates we apply in sequence, is also correlated to how long my algorithm is running. Remember, the further you go in the circuit, the more time you're spending in it. And the more time you spend in it, the more chance for errors to occur. So we cannot run very deep algorithms, because noise is essentially going to kill off our computation. So we're limited in the capability of depth. And some of the actual quantum devices that we have, again, as we said, there's many physical realizations. Xanadu is working on photonic quantum computers. A company called IonQ works with trapped ions. And maybe the most famous ones are superconducting qubits. IBM, this is actually outdated now. Just a couple of weeks ago, IBM announced their new processor with 100 and something qubits. They actually have cloud access, which is really nice, because that means that you can just access the quantum computer from the cloud. There's Google quantum computer, which is also made out of superconducting qubits. There is the Zhuangqi superconducting qubits quantum computer developed in China. And there's also Rigetti superconducting quantum computer. Of course, I'm missing a lot of quantum computers and a lot of implementations. But this is just to say that there's a lot of companies, nations, and universities that are working very hard to improve the technologies that we have today try to build larger and better quantum computers. So what is the problem with the textbook algorithms that we're previously seeing in the NISQ era, like Shor's algorithm for factoring, or Grover's algorithm? Can we use those quantum computers? If we have this one right here, 72 qubits, this is a 2 to the 72 Hilbert space. This is extremely large. So can we use that quantum computer, for instance, for Fourier transformations or for breaking the RSA encryption system? So the question is that no, because we can't really implement the textbook algorithms in NISQ devices. And let's take a very specific example. Let's think about the quantum algorithm for solving linear systems of equations. So this is a beautiful paper by Aram Haro, Anivatan Hasidim, and Seth Lloyd, where they show that you can use quantum computers to solve the classical linear systems of equations problem. But of course, the problem about this is it's an algorithm that uses very deep circuits. And there was this paper that did a concrete resource analysis of what it is that you need, like physical-wise, to be able to solve a given problem size. And what they saw was that this blob right here that you need, for instance, for 28 qubits to solve this matrix, this blob right here is actually a quantum circuit. And if you zoom in, you can actually see some of the gates that are implemented in there. And this is because this circuit uses what we call oracles, which are just black boxes that is just a unitary that is doing something. We know how that unitary works, but then whenever you're trying to implement that part of the quantum circuit, it is extremely deep. And whenever we try to see what the actual requirement is, we need a circuit depth of 10 to the 29. And we need a number of extra qubits, which we call ancillary or auxiliary qubits, that are of the order of 10 to the 8. And this makes it such that implementing the HHL algorithm in the near term becomes extremely complicated. And the first time that we made this talk, the largest system that was solved in a quantum computer using this algorithm was 2 equations and 2 unknowns. I believe that was pushed to 16, but still 16 equations and 16 unknowns, you can probably still solve that by hand. So this is not an algorithm that we can implement in the NISQ era. We just cannot, because it has some circuit requirements that are well beyond the NISQ era. So of course, the problem here is noise. We're limited in the qubit size, but of course, by noise in the circuit depth. So people might ask, what about quantum error correction? So quantum error correction is a framework that is used in quantum computing to protect information from errors due to decoherence and other sorts of quantum noise, or my system interacting with the environment in an uncontrolled ways. This has been developed in classical information theory. Whenever we have classical information transmission, we might have errors, and we want to try to correct for those errors. So there's been a framework that has been developed for correcting errors in quantum devices, and it's actually been shown that we can correct to an arbitrary level single qubit quantum errors. This is really nice, because this means that we can actually take qubits and get the error out of them, so that we preserve the information that we want to encode in those qubits. So similar to classical error correction in classical computing, quantum error correction codes for error correction, for instance, can create redundancies, where instead of encoding the state of the system, the state of the qubit in just one physical qubit, we encode it in multiple qubits, and we leverage entanglement to detect and correct syndromes. So for instance, if I want to encode a state psi into one qubit, I can always encode this state into 3 qubits. And what I do is that this code right here is going to protect me from bit flips, just randomly my 0 becoming 1 and my 1 becoming 0, so that at the end, I can recover my state psi. So the main idea is, this is what we call physical versus error-corrected qubits. This all right here, these 3 physical qubits, like 3 lines, are essentially going to be giving me 1 error-corrected qubit against bit flip errors. So the idea of quantum error correction is that we are going to take a lot of physical qubits, and we're going to encode them into logical error-corrected qubits. So multiple physical qubits make small number of logical error-corrected qubits. And for instance, the question has been asked, if we want to factor 2048-bit RSA integer, which is again for encryption, we would need 20 million noisy qubits, because again, we need to encode a lot of those qubits into error-corrected qubits, and we just don't have that that quality right now. So we don't have enough qubits. And of course, that's this 20 million noisy qubits. How many qubits, how many physical qubits we need per logical qubits depends on the noise level. The less noise we have, the less physical qubits we have. So this is a pretty old paper. It was using very noisy results for quantum computers. So, this can be improved. But still, the problem with error correction is that you need a lot of physical qubits, and we don't have that many physical qubits. We just have quantum computers with hopefully hundreds of qubits. So we can't yet implement quantum error correction. So this is what splits quantum computing into two, what we call fault-tolerant era. And this is where we assume that we can run error correction to get rid of errors in our qubits, and the NISQ near-term era, where we're still trying to get the best out of our noisy quantum computers. So in the fault-tolerant era, we're going to be able to reliably prepare qubits and implement quantum operations, whereas in the NISQ era, we're going to have errors in both our qubit preparation and gate implementations. In the fault-tolerant era, we're going to have devices with thousands or even millions of qubits. Here, maybe a few hundreds of qubits. We can implement error correction in the fault-tolerant era. We can't implement that yet because, again, we're limited in the depth and the size of the algorithm. And this makes it so that we can't implement a lot of textbook algorithms. So, as we said, we don't have enough physical qubits. Something that you might ask is, well, why don't we just build more qubits? It's building more qubits so that we can implement, redundancies and error correction, the solution. Well, it's not that simple because the number of qubits is not the only metric. So if we have a lot of qubits, but those qubits are very noisy, that's not going to help us still. We need good quality qubits to be able to do something useful. So we don't just need a lot of physical qubits, we need their errors to be small. So we need to be in a range with small errors, high numbers of qubits. And this is where maybe we can get something here in the near term. And once we reach enough qubits with small enough error rates, we're going to be able to do error correction. So this is the main idea. This is the path forward. But of course, we're still not there. We're somewhere around here. And the question is, can we still get something useful out of NISQ devices? Can we still try to use near-term quantum computers to outperform their classical counterparts? And the question is, and the solution to this is, of course, yes. Otherwise, we wouldn't be here. And so where can we expect to get some advantage of using noisy quantum computers? So we know that we can think about a foundational science perspective. Because despite of their limitations, current quantum devices already allow us to probe the very nature of individual quantum systems to a level in which we haven't had access before. This is an unprecedented access that we have to controlling individual quantum system and testing the limits of our theories, of how those interact with each other, with the environment, of how they can process information. So that's already something extremely interesting. But of course, we care more about a computational perspective because, and for instance, you might have heard that in 2019, Google achieved the first quantum supremacy experiment, where a quantum computer was used to solve a contrived mathematical task faster than any classical algorithm. And this was all over the place. It was all over the news. Financial Times, Google claims to have reached quantum supremacy. News scientists, like science divulgation media. And, it started to get off the board because people started to hear about quantum supremacy. So news and the internet, of course, make a very weird combination. So, Google achieves quantum supremacy that will render all cryptocurrency breakable, all military secrets revealed. Maybe not. And of course, the internet is a very interesting place, very well stuffed. Paperlink, quantum computer supremacy. They're not building computers, they're building gods. I mean, sure, there's a lot being said about quantum computing, quantum supremacy. Let's try to unpack it. Let's just leave the internet on the side because it's a wild, crazy place. So this is what Google actually did. This is the problem that they had. They want to generate a random quantum circuit, apply it to an initial state, and measure some elements from the output distribution. So they just want to measure the qubits at the end. As we know, we have 2 to the n possible outcomes, and they just want to see this distribution. So it's been proved that the distribution should converge to what is called as the Porter-Thomas distribution, where there is the probability of those given bit strings sort of follows in this way. There are some bit strings that are more probable than others, and they wanted to show that their machine actually converges to this, because the Porter-Thomas distribution is actually quite sensitive. So if you have a lot of noise, this will actually break. It will break pretty badly. So this is what Google did. They actually showed that their device follows the Porter-Thomas distribution. So they were able to do this task, and just sampling this and trying to simulate this classically is an exponentially difficult task. You cannot do this classically because it's really expensive. And the question is this useful for something? Well, not really. It's not obvious. It's just some mathematical task. And this is why we call this quantum supremacy and not quantum advantage. Quantum supremacy is just, let's do something mathematically faster than any classical algorithm. So did they manage to do something at that point faster than the best classical algorithm? Yes. Are they building gods? Most surely not. That is for sure. So this was indeed a milestone. And of course, as with all computational science, you can always compare algorithm to algorithm. As we said, you have to take your best classical algorithm, your best quantum algorithm, and compare their complexity. So has the Google supremacy result holding up ever since then? Well, no, but that's okay, because as we know, in 2019, Google claimed in their paper that their quantum processor takes about 200 seconds to sample one instance of a quantum circuit 1,000,000 times. And what they were doing is comparing against the best classical methods, and they said that the state-of-the-art classical supercomputer would take approximately 10,000 years to be able to solve the same task. But recently, and again, extremely recently, October 28, 2021, so just a month ago, there's been new classical algorithms that have been developed, and they provide a new milestone for classical simulation of quantum circuits. And they reduce the computational complexity to simulate the outcomes of the Google Sycamore experiment to just 304 seconds from the previously claimed 10,000 years. So this is something that happens a lot. There's always a classical and quantum push that are naturally pushing back to develop better algorithms that are going to compete. And this is good because they're improving each other. We're getting better classical algorithms to try to reproduce quantum results. Of course, this was with, I believe, 54 qubits. If you were to do this with 100 qubits, then the classical algorithm will probably, again, fall apart, and we need to develop better classical algorithms. But sure, at the end of the day, what we care is that quantum supremacy, it was already broken at some point. It was caught up by classical methods, but it solved a mathematical task that had no immediate implementation or application, no practical application. Now we want to use quantum computers for what we call a quantum advantage. And this means using a quantum computer to solve a practical task of scientific, engineering, or economical interest faster than any classical supercomputer. And this is what we care for. This is precisely what we want to use quantum computers, because we don't just want to do something classically hard to do in some mathematical task. We want to do something that is going to be of interest for society, for science, for engineering. So how are we going to achieve this in the near term? And this is where we start to get closer to quantum machine learning, which is hybrid methods. And what we're trying to do is we're trying to pair NISQ quantum computers with classical computers and have them working together rather than collaborating, competing before. We want to get the best out of both worlds, where we still use a noisy computer to do something that is classically hard, but we also push some of the computational complexity onto classical algorithms so that we can try to get the best out of both worlds. So let's talk about a little bit about near-term quantum computing models. So of course, what we want is we want to account for all the constraints imposed by NISQ computers. That means limited number of qubits. That means limited depth. So, and of course, what we can think about here is that accounting for all of those limitations almost naturally is going to require an optimization-based or learning-based approach. So here, what we're going to try to do is, again, because we said we're trying to push the complexity into onto classical computers, coming up with algorithms that are going to be quantum classical could be hard, right? So let's try to have the classical computer solve the problem for us. And this is why we mean about like the learning-based approach. So in general, all of the near-term quantum computing models are going to be of the following way. We're going to take a problem or a task of interest, and we are going to encode it in such a way that we can use a quantum computer to evaluate quantities that are difficult to evaluate classically. And we're going to use classical optimizers to train my quantum computer so that we can solve these tasks. And this is completely analog to what we do in machine learning, right? We encode a task of interest into an optimization problem. And this is the framework that we're going to be working with for the rest of this course, the framework of variational algorithms and quantum machine learning. So what do we have here? Here we usually have some problem of interest, and we're going to be able to define this. We're going to encode the problem of interest into what we call the cost or loss function, which is a function that quantifies how well or how close we are to solving our task. Then we can have something like training data that we're going to be using. Then we can also have something as an input as, and this was a question that was asked during Amira's talk, and we're going to get into more detail. Maybe we want to use a parametrized quantum circuit. How are the gates placed in this quantum circuit? What is the ansatz? What is the assumptions about the structure of the parametrized quantum circuit that we're doing? And again, here what we do is that we're going to take, for instance, our quantum data. Those can be quantum states. We're going to send them through a parametrized quantum circuit. We're going to make measurements. With those measurements, we're going to estimate our cost function. That is a function that depends on the set of trainable parameters, for instance, in my circuit. And we're going to have our classical computer optimize this cost function in the sense that we want to give it a set of parameters, and we want the classical computers to give us an updated set of parameters that gives me a better cost function value, maybe smaller, because I'm trying to minimize the cost function, and smaller cost function values means I'm closest or closer to finishing the task. So essentially, you can always think about the optimization process as navigating through some landscape, because for each set of parameters in this hyperparameter space, it defines me one real valued cost function. So different set of parameters give me cost function values, and you can think about this as some hypersurface in some higher dimensional space that I'm navigating, and I'm trying to get to the global minima. Once I find the global minima, if I did a correct work and I was able to encode my problem such that the global minima corresponds to the solution of the problem, then I have finished, and I have solved the problem using quantum and classical computers. And of course, the output of the algorithm is going to depend on the task at hand. Maybe we're trying to prepare a quantum state. Maybe we're trying to prepare the ground state of some molecule. Maybe it's a probability distribution or a single bit string. Maybe we want a gate sequence. That's the solution to a problem. We're going to see different examples of algorithms where the output is going to be different. So first, let's talk about variational quantum algorithms. This was maybe the first widely used approach to near-term quantum computer. And this is very analogous to traditional programming in the sense that it is task-oriented, where a user or the researcher is going to manually formulate or code the rules of the algorithm. What does this mean? This means that we're going to have an input that can be, maybe we want to find the ground state of a given molecule. We're going to write an algorithm that is going to minimize that problem, and it's going to give me an output that could be my state. So this is the way in which classical programming works. We have an input, we write a program that we wrote by ourselves, and we get a desired output. But there's also a way to generalize this into what we call quantum machine learning. And this is it maybe recently has received more attention as the framework for near-term quantum computer, because analogous to classical machine learning, what we do here is that we automate the learning process, where what we have is that we have an input and an output, and we have the model give us the program. So this might not be obvious what we mean by this now, but hopefully by the end of the course, you're going to see what is the difference between these two, and why do we care about quantum machine learning, specifically maybe most in the near term. So let's just give examples of variational quantum algorithms and quantum machine learning, because this might not be obvious. So let's go to some specific examples. So, and actually, before going that, is there any question in chat at this point? Do people want to ask anything? I'm not able to currently read chat. Let me just go to here. Let's see. Oop. If you have any question, feel free to unmute yourself or interrupt me. If not, I will just keep going. So let's think about the first and perhaps most famous variational quantum algorithm, which is the variational quantum Eigensolver. So here the input is we have an n-qubit Hamiltonian that describes the interaction of some physical system. And we're usually going to assume that we have it described in some form. And the goal is to find the ground state of this Hamiltonian. Maybe what we want to try to do is to prepare a quantum state such that it's the ground state of this Hamiltonian. Now, why is this important? Because imagine that the Hamiltonian represents the interactions of a protein, and we want to see what's the stable state, the ground state of that protein, because maybe we want to try to synthesize it in the lab, and we want to know if that protein is going to have some properties. Well, the properties are going to depend on, first, if it's in the ground state of that Hamiltonian, and then once we have found the ground state, we can analyze some of the properties so that we know if maybe that protein is going to interact with some drug or with some receptor in the body. So we want to try to do some principled study before we go and invest in synthesizing it and studying, because that's usually more expensive. So the way that the variational quantum eigensolver algorithm works is that, again, let's just follow the De Vincenzo criteria. We're going to initialize our qubits in a simple state. Usually it's just going to be the 0 state, but as we're going to see later, this can be more complex. We're going to send them through a parametrized quantum circuit whose action is to prepare a quantum state that is going to be parametrized, and which is simply given by, I take my states, send them through the parametrized quantum circuit, which applies a unitary to the states like this, and it gives me a quantum state here of this form. Then we're going to measure the expectation value of this Hamiltonian over this state, and we're going to do this using a quantum computer. So usually, maybe measuring the expectation value of the whole Hamiltonian is hard. So what we're going to do is that if we have some expansion of the Hamiltonian into a simpler basis, we're just going to compute the individual expectation values, and then with classical computers, just build this whole summation right here. Then we're going to use a classical optimizer to update the parameters, and our output here is going to be a circuit, U of theta, that prepares the ground state of our state. If we manage to solve the problem, what we have is a circuit that, once I put it here, the optimal set of parameters, I have a guarantee that at its output, I'm going to have the ground state of the molecule that I want. So this is an example of a variational quantum algorithm. Now let's think about a quantum machine learning example. For instance, we can think about quantum state classification. So
I'm sorry. May I have a question?
Absolutely, yeah. Please go ahead.
Yeah. So, for example, you mentioned that the kind of Hamiltonian that we can employ is on the form on the decomposition that you have shown there.
Yes.
So, is there any limitation to the kind of Hamiltonian that we can analyze that may have that form, or we can, I don't know, using some procedure, just try to transform any Hamiltonian into that form?
So yes, and we're actually going to see this in more detail, I think, in our tomorrow class, where, for instance, let's think about what I was saying, like a molecular Hamiltonian. If you think about quantum machine learning course and the way in which you usually write Hamiltonians, they're written in momentum and position operators, P and X, right? And it's not obvious how to measure the expectation value of X or P. So usually what you have to do is make a series of transformations that are going to map that Hamiltonian to a qubit Hamiltonian of operators that I can measure efficiently in a quantum computer. So yes, that means that there is a lot of work that takes into getting a Hamiltonian that I'm going to be able to efficiently get the expectation value of in a quantum computer, because maybe this step right here is not efficient, and then I'm already screwed, right? Because if I cannot efficiently implement this, I'm going to have a problem. Luckily, it's been shown that a lot of problems of interest in both quantum chemistry, condensed matter, and more generally material sciences, you can always map Hamiltonians to a simple form where those H's are going to be, for instance, Pauli operators, just a tensor product of Pauli operators. And this summation right here is going to have a polynomial number of terms. Because, for instance, and this is actually a good question, imagine that you do some mapping and you get some Hamiltonian, but this has an exponential number of terms. This means that here I'm going to have to run my quantum algorithm an exponential number of terms times to estimate all of those terms. So I will not be able to have an efficient variational algorithm for that Hamiltonian, because this part right here is going to be an issue. So yes, you have to be careful about what are the Hamiltonians that you can implement a variational quantum algorithm on. Locally, a lot of Hamiltonians and problems of interest will have an efficient decomposition.
Thank you very much for that answer.
All right. Thank you very much for the question. That's a great question. So let's go back to quantum machine learning. As I was saying, we can think about one implementation like quantum state classification. And by the end of this course, as you know, we're going to have in the afternoon some hands-on sessions where we're going to do some theoretical and coding Python exercises. If you manage to do everything by the end of this week, you should be able to code a quantum machine learning example to classify quantum states. So this is actually going to be extremely relevant for the hands-on sections. So similar to classical machine learning, we can think about a classification supervised learning task. So here, what we're going to have is a data set of, maybe we have an n-qubit Hamiltonian, and this Hamiltonian has several phases. All right. Yeah, please read it. So maybe I'm going to ask a question back. What do you mean by the distribution of the Hamiltonian? Maybe I'm going to give whomever asked the question a couple of seconds to just follow up, because I don't want to answer anything without being sure what the question is about. So what do you mean by the distribution of a Hamiltonian? Right. So yes, there's several things that we can do, not necessarily just find the ground states. So for instance, you can also find like the thermal states of a given Hamiltonian. And in that case, you're going to have a distribution. So yes, there are different algorithms that you can do that are going to extract different information about this Hamiltonian. You can also try to find what is the distribution of eigenvalues of this Hamiltonian. There are things that you can do that are not necessarily finding the ground state. This is just one example of the Hamiltonian. But you can also think about, for instance, like a max end problem, where you're trying to find like the given thermal state that satisfies given probability distribution for a given Hamiltonian, and you're trying to prepare that state. So it's way more general than this. This is just one example of one variational algorithm. The only question is, if you can encode that task, for instance, the distribution of the Hamiltonian into a cost function that is efficiently computable, then there could be a variational quantum algorithm. And that's precisely what I was saying about why variational quantum algorithms are task-oriented. Because you have a problem, say I want to find the Gibbs state of a given Hamiltonian. I need to encode that myself into a cost function that I'm going to be able to minimize. And I need to know that cost function is going to be efficient. So that's why in the previous section, we had this idea of input, program, output, because you need to be able to come up with the cost function that does that. I hope that answers the question. If not, you can just ask in chat and we will follow up on that. But what I was saying here is that imagine that we have a Hamiltonian that has several quantum phases. For instance, here you might have a Hamiltonian that, depending on the doping and temperature, you might have superconducting phases or antiferromagnetic phases, or maybe like strange metal or insulator phases. So what we want to do here is, we can always sample ground states of this Hamiltonian from different phases, and we're going to have a set of states, each one with their labels. For instance, maybe I'm going to have a set of states from this phase, and I'm going to label each one of them state with a label superconducting. And maybe I'm just going to sample in an isolator phase, and I'm going to have states that are associated with a label insulator. And what we can do now is, try to train a model that is going to classify those states according to their phase. And note here, interestingly, that we can combine variational quantum algorithms with quantum machine learning. And this picture right here is essentially what the coding exercise is going to be for this course, which is we're going to use VQE to prepare the ground states of a model that have different phases. And then we're going to send those states through a quantum neural network to classify them. So first we do the training for state preparation, and we're going to know that we can prepare states with associated labels, and then we're going to send those through a quantum neural network that we're going to train to do the classification. So here, the goal is train a quantum machine learning model that is going to be a model that maps states to labels over the data set. And the information processing task here is done by a quantum neural network, which again is going to be a form of parametrized quantum circuit. And we're going to encode this problem, for instance, in a mean squared error or log likelihood loss function. So those are loss functions from classical machine learning that we're going to train and we're going to use to train our classification problem. So, and here the output is a quantum neural network program that can classify phases of matter, because then I can give it a state that I don't know where it is from, and I can try to predict if it's going to be superconductor or non-superconductor. And that's the idea of using, for instance, quantum machine learning for quantum data. Again, you can also think about quantum machine learning for classical data, but here we're talking about quantum machine learning for quantum data. So again, you can see that the learning approach and the learning methodology of machine learning is extremely natural for quantum data, because again, quantum mechanics is very counterintuitive. And if we have to design a circuit that classifies states according to their phase of matter, that could be very hard, but maybe we could just have the algorithm train it by itself. And more generally, variational quantum algorithms have been already considered, and I think this plays back to the idea of what can we use a variational quantum algorithm for, if not just finding ground states. Well, variational quantum algorithms have been envisioned for a wide range of applications. And we have essentially a one-to-one mapping between all the fault-tolerant algorithms and a variational algorithm. So that what we have is that essentially everything that we want to get out of a quantum computer, we can try to get that out of a near-term quantum computer in a variational framework. So again, we can think about performing simulations, which was the original Feynman idea. We can think about finding ground states. Those can be for quantum chemistry or condensed matter. For mathematical applications, like solving linear systems of equations, factoring numbers, performing principal component analysis. Also, we can think about variational quantum algorithms for classical data, like solving combinatorial optimization problems. For probing and studying the new frontiers that quantum technologies allow us to do, like studying quantum information processing tasks in quantum devices, quantum metrology using quantum systems as sensors. We can think about the foundations of quantum mechanics. Again, we can think about machine learning, classification, generative models. We can think about how to transform data into quantum circuits that are going to be useful. And we can also think about how to use variational quantum algorithms to improve our error correction codes, or to develop what we call error mitigation codes, that we can somehow still try to get rid of the effect of errors. So we can also think about more general quantum machine learning applications. And quantum machine learning is just like classical machine learning, a very broad term. And this is the picture that you've already all seen from Amira's talk. We can think about quantum machine learning as encompassing all of those cases where we have data and algorithm. And our data can be classical or quantum. Our algorithm can be classical or quantum. And all of this can be thought about quantum machine learning, even classical data, classical algorithm. So you can think about, for instance, as the quantum-inspired algorithms. Those are algorithms that are based on the laws of quantum mechanics, that we can somehow try to embed those into a classical algorithm to deal with classical data. We can also think about quantum data with classical algorithms, using Monte Carlo to find the ground state of a molecule, right? This is an algorithm that would fit here. We're using quantum data, quantum states, that our algorithm is classical. But for us, more importantly, we're going to be focusing here, where our algorithm is going to be quantum. And for instance, we can use that quantum algorithm for classical data. For instance, for factoring numbers, or we want to classify pictures of dogs and cats using a quantum computer. Or we want to also have a quantum algorithm for quantum data, like finding the ground state of a molecule, or classifying states, quantum states, according to their phases of matter. So these two sorts of algorithms are usually going to have this structure right here. So first, let's think about this top left. So we have classical data, quantum algorithm. And again, we're going to go into way more detail about this once we go into the blackboard, but this is just a bird's overview. So classical data, imagine a supervised learning task of classifying pictures of cats and dogs. So I have a picture that is usually a collection of bits, and I have a label, cat or dog. So what I need to do first is that, my quantum computer cannot deal with this classical data. I have somehow to embed that information into a quantum state that my quantum computer can work with. So usually whenever we're working with classical data and quantum algorithms, we're going to require a data embedding scheme, where we're going to take our classical data, we're going to run it through some scheme, and that depends on that classical data, and we're going to get a quantum state at the end. Whenever we have quantum data, again, maybe we're trying to tell apart ferromagnetic from paramagnetic states from a spin chain, what we're going to have, it's already in the quantum form. So by the end of the embedding, or just here, we usually have something that looks like this, which is quantum data and labels. Here for classical, again, we embedded it. And then we're going to use a model that is going to be usually a quantum neural network, where we're going to send these collections of states. We're going to perform measurements out of those states, out the output of the quantum neural network, and we're going to create our loss function to classically optimize and try to use this hybrid methodology and iterate until we find the solution to our problem. So this is essentially what we're going to be working with. And you might ask yourself, like, why would we ever want to do classical quantum machine learning for classical data? Why do we expect this to work? So this, and Amira already hinted a little bit to this in her talk, because we can think about quantum models as kernel methods. For people that are versed and familiar with classical machine learning, you know that whenever you're using the kernel trick, you're going to take your classical data, embed it into a higher dimensional space, where you're going to try to perform operations of your data into that higher dimensional space to solve your problem. And this is essentially the same idea of quantum machine learning. The Hilbert space is very large. It's exponentially big. So it sort of works like a kernel, where I can use all of the support vector machine tricks that people use in classical machine learning. And it's just that the feature space where I'm embedding my classical data is just going to be a Hilbert space. So this is a little bit the idea of quantum machine learning for classical data. So now, again, just going back to comparing variational quantum algorithms and quantum machine learning. Here, usually in a variational quantum algorithm, our input is just going to be a simple state, like the old zero state. We usually don't think about training data for variational quantum algorithms, like in VQE. If we're trying to find the ground state of a molecule, we usually don't have training data. We don't have anything like that. And we usually minimize a cost function that is going to be linear. Oh, I'm missing here an operator H, like minimizing the ground state of H. So excuse me about that. And we're going to train a parametrized quantum circuit. Quantum machine learning, again, our input is non-trivial states. Those non-trivial input states can be the ground states of molecules or classical data that has been embedded into quantum states. And we usually think about having training data. And here we minimize the loss function that is usually non-linear in measurement outcomes at the end of my quantum computer. So this can be like a mean squared loss function or the log likelihood loss function. And we're going to train a quantum neural network. So parametrized quantum circuits and quantum neural networks, they are essentially the same. It's just that we tend to use quantum neural networks for the case whenever our circuit is processing data. So that's why we use the terminology quantum neural network in analogy to the classical use of the word. So let's now think about these two models in the overall picture of quantum computing. So we're here in the noisy intermediate scale era, where we have quantum computers that are limited in qubits, they're error prone and whatnot. We will eventually have partial error corrections, and hopefully in the not so long future, fault tolerant quantum computers. So, variational quantum algorithms, it's obvious that they're going to be useful in the noisy era. In the partial error corrected era, for sure too, because here we're going to be able to run algorithms with higher fidelity, because some of our qubits are going to be fully protected against errors, right? And the question of will variational quantum algorithms be useful in the fault tolerant era, it's still up for debate. I believe that they will be, because we're going to have very large quantum computers, so we're going to be able to implement very large variational quantum algorithms where we use the physical qubits maybe instead of the logical error-corrected qubits, right? But of course, the thing about quantum machine learning is that it's always going to be useful, because here in the near term, we can try to use it to probe the capabilities of near-term quantum computers. And in the fault-tolerant era, imagine that you can prepare the ground states of molecules without VQA. You can use a quantum simulation algorithm to get those ground states, no optimization needed. Well, maybe we still want to try to learn from those quantum states. And again, the thing is that writing algorithms for analyzing quantum data is very counterintuitive. So the learning framework of quantum machine learning is going to be absolutely and more than ever used in the fault-tolerant era, because quantum data is going to be easily produced here, and we're going to have to deal with that quantum data. We want to do something about it. We want to learn from it. And the quantum machine learning framework is completely natural. So this idea of, training quantum neural networks is always going to be here, both in the near-term era and also in the fault-tolerant era. So hopefully the tools that you're going to be learning in this course are going to be useful not just in the near future, but all throughout the history of quantum computing, if this is something that you're interested in. So, of course, the question, and going back to the original efficiency, is VQAs and quantum machine learning models are heuristic models. So the question is, can we somehow try to guarantee a speed up with quantum machine learning and variational quantum algorithms? And this is the big elephant in the room. This is the question that everyone is trying to answer now. So, of course, we have to be completely honest and say that provable complexity results for variational algorithms and quantum machine learning models are usually case-specific, which means that they will apply for one specific task with one specific problem with one specific type of data, and they're usually hard to come by. And recently, there's been a lot of effort to try to understand what are the capabilities and limitations of near-term hybrid quantum computing models. And this is an absolute open question, and this is something that we're extremely interested in working in, because we don't know the answer. That's the honest solution that we can give now. We don't know what are the limitations and the capabilities of hybrid near-term models. There's been a lot of work in this, as you saw already. Amira, she was telling you about the power of quantum neural networks. But there's also a lot of very interesting work trying to prove bounds on what is the advantage that you can get in quantum machine learning. And there's a lot of very recent papers in this field. So given that, maybe, and this is starting to wrap up with this PowerPoint presentation, I hope that this wasn't too much for the first day. Let's try to give an overview of where the field currently stands. So again, there is a great deal of hope that we can achieve quantum advantage with variational quantum algorithms and quantum machine learning. We still have to prove it. There are some hints here and there of where we could actually get that advantage. There's also hints of where we're not going to get it, and we're still trying to work that out. But there's definitely a great deal of hope. And of course, we know that hardware improves every day. Just a couple of weeks ago, IBM announced their new machine, and we can definitely expect better and larger devices. And again, it's not just the qubit count, it's the error rate that also counts. But also, there are still many unanswered questions, and there's a lot of work that needs to be done. For instance, how much does noise in quantum hardware limit the usability of quantum algorithms? There are like 3 questions about this that were asked to Amira in our previous talk. So this is definitely interesting, because again, we cannot create a quantum algorithm without taking into account noise, because that's the whole point of near-term quantum computing. So again, and how can we guarantee that we can actually train the parameters in that parametrized quantum circuit or quantum neural network? How do I know that my classical optimizer will be able to give me a good set of parameters that gives me a good solution? Can we guarantee that even if we train, the model will generalize well? Because that's the whole point. I want it to perform well on unseen data, on cases that it's not previously looked at. And as Amira said, this is still an open question that we're exploring. And again, how is quantum machine learning different than classical machine learning? Where is the quantum advantage coming from? And how can we expect to have a quantum advantage? What are the ingredients that we need? For instance, we also can ask the question, will quantum machine learning be better with classical or quantum data? We still don't know, right? We don't know where the advantage is going to come from. I personally believe that quantum machine learning is better suited for quantum data, because classical data, we have very good classical algorithms, and trying to compete with those with noisy computers does seem like it might not be the way to go, right? So, and what we need to do here is that we need to develop, for instance, whenever we're dealing with classical data, quantum-aware encoding schemes to map that classical data to quantum data. We also need to develop quantum neural network architectures. And there was a question about this too, and like, are there like one type of neural network? Are there many? Well, there's a bunch of them. Essentially, every classical neural network has been quantized, and there's like a quantum version. There's like the quantum GANs. There's like the quantum convolutional neural network. We also need to improve our optimizers, because it's been shown that the optimizers using classical machine learning, they underperform with quantum machine learning. And the same with loss functions. We need to develop loss functions that are quantum aware. And this is all to say that even if machine learning in classical machine learning has been so well developed, we can't simply rely that classically developed methods will perform well in quantum. We need to do a principled analysis to try to develop quantum aware and quantum specific methods. So, my mentor, Patrick Coles, has this quote, which I really like, which says that after the invention of the laser, it was called a solution in search of a problem. And to some degree, the same happens with quantum machine learning. So this is to say that we have this framework. There's still a lot of questions. We don't know where it's going to give us a quantum advantage, that we're going to be able to use it to get a quantum speed up. So it's definitely a young field, an exciting time with many unanswered questions. And of course, what we need to be thinking is we need to take a cool-headed approach to near-term quantum computing. Because, again, the media does this dangerous thing that there's a lot of hype for quantum, and some of which is justified, some of which maybe isn't, and it might be blown out of proportion. So from my perspective, and this is especially for the younger students in this course, the question is, all right, so quantum machine learning, what is it? So for me, it's a new tool that you're going to have under your belt. If you're interested in research, maybe in industry, it's a tool that you have to be aware of. Are you going to be able to use it tomorrow to solve something and improve your workflow? Probably not in the near term, but that's not something bad. That's something good. That means that there's research to be done. That means that there's questions to be answered where you yourself can be answering those questions. And of course, what we need here is that, again, we need a principled analysis. And this is going back to what this course is going to be about. And I'm going to get into more of that in a second, because we cannot settle on heuristics or just numerical experiments that work on small examples, but maybe are going to break once larger training sets are employed, right? And this is going back to the historical development of classical neural networks, because when they were developed, they were, despite the fact that classical neural networks and machine learning is used widely throughout all areas of science today, at the beginning, it wasn't obvious what neural networks were for. And in their development, there were periods of great stagnation where neural networks were not used because it wasn't clear what they were useful for. The first single perceptron was developed, and then it was realized that multi-layer perceptrons were more powerful, but harder to train, and the backpropagation method had to be developed. So there were like those winters and periods of stagnations in classical machine learning. And the question that I'm interested in and that I want to try to answer is a quantum neural network coming? Like, can we see the signs? And of course, because more importantly, let's try to make sure that we're not heading towards a quantum winter or a quantum bubble. So this is, I think, that the overview that I wanted to give people about the field in itself, like just, take a step backwards, look at the whole field and trying to understand what people are doing, what they're interested in, what the different questions are. But now let's just focus on this course. So I think that every time that I've taken a course and I've had someone do this, I've found it really useful, which is, what can you expect from this course? What is this course going to be about? I want to try to manage expectations for people that are here. And I want to tell them this is what to expect. And this is what I think that you can get out of this course. So again, while quantum machine learning has the potential to be a groundbreaking and revolutionary tool, and we know that it can impact scientific research, industrial applications, economy, cybersecurity, as I said, will it be available in the next couple of years? Probably not for practical use, but definitely yes for basic science research. So we can expect theoretical and experimental results to improve our understanding of quantum machine learning. And how does this fit into this course? So this course is mainly going to be about theory. And I think that's the first thing that you need to know. There is going to be a lot of theory, a lot of pen and paper. This is not going to be a coding course, because whenever people talk about classical machine learning, nowadays people don't study the learning theory. They don't learn the statistical theory behind the learning methodology. They just go, they learn to use keras, they learn how to load a data set, they learn how to just use a bunch of tools that have been developed from them. And we're not at that point yet in quantum machine learning. The field is way too young for that. We don't have the quantum keras, or maybe there are some versions, but we're not going to use them because I want people to understand the very basics. Why? Because if you understand the basics behind quantum machine learning, the basics in quantum mechanics, the basics in learning theory, in statistical theory, you're going to be able to understand the improvements that are being done, and maybe you will be able to do some research in this field. So in that sense, we're going to take a theoretical and principled approach to quantum machine learning. So that means that we're gonna, and because quantum machine learning stands at the intersection of many fields, we're gonna be talking a lot about the basics of quantum mechanics, quantum information, and machine learning. So that means that we will cover an introduction to all of those fields. And those basic tools that we will see are going to be useful to understand the current state of research. And again, hopefully allow you to incur in the field and do some research by yourself. So that means that there's going to be some theoretical exercises and hands-on exercises. The theoretical exercises are going to be essentially the basic framework for quantum machine learning. And the first theoretical Blackboard class is going to be reviewing the principles of quantum mechanics from a modern perspective. That might seem, redundant if you've already done a machine learning course, maybe even boring, but you're going to see that having a firm grasp on those simple principles is going to allow you to use all the quantum machine learning tool work and framework at your disposal. So we're going to take that principle approach. Then for the hands-on exercises, again, this is the goal. And I'm just going to put it right in front of you. And you're going to have access to the whole code with all of the exercise from the beginning of the course. And the same with the theoretical exercise. The idea of this course is for you to go at your own pace and you to try to get the best of it, of what it is that you want. Maybe you're more interested in the theory and you just want to run through the theoretical exercises. Maybe you want to go into coding and you just want to jump right in it. Well, for coding, we're going to do first a VQE implementation. We're going to be finding ground states. And then we're going to use those ground states to create a data set that you're going to be classifying using a quantum neural network. And this is all ground up. That means that while there are some packages out there that allow you to do some black box things, we're not going to do that. We're going to code everything from the ground up because, again, I think that that's the important thing for this course. It's a young field, and that ground up work is still extremely valuable, and I think it'll be in this course. So I think that with that, I'm just going to start wrapping up. I want to introduce you to Subhadra Echeverria and Felipe Choi. They're going to be the teaching assistants that are going to be working with me throughout the course. We're going to be splitting in some sections. Some of you are going to be working with me. Some of you are going to be working with them. They're really well prepared. I've been working with them for the past couple of months, getting them up to speed in the theoretical and hands-on exercises. They're great. And we're going to send this via email, but here in this GitHub repository, you're going to be able to find all the theoretical exercises and the notebook for the coding exercises. So again, we have 3 hours in the afternoon. You go at your own pace. The more you put into it, the more you're going to get out of it. And of course, I couldn't finish without some suggested reading. So if you're more interested and want to dive deeper beyond what is going to be taught in this course, if you want some basics for quantum computing, of course, the basic is Nielsen and Chuang's book, Quantum Computation and Quantum Information, beautiful book. You want to learn more about quantum information, I recommend Mark Wilde's book. It's called Quantum Information Theory. These two are available online, so you can just find them. This is the archive link for this one. You just Google the name, and it's also available online. If you want to learn more about quantum machine learning, Maria Schultz has this book that is called Supervised Learning with Quantum Computers. There's also a review by Jacob Viamonte that is called Quantum Machine Learning. You can find the archive link in here. You want to learn more about variational quantum algorithm, here's 3 very recent reviews about the field that are going to give you like a brief overview of everything that's being on and what people are interested in the field. And I think that with that, I want to thank everyone for your attention. The next step is we're going to get a pen and paper class. I believe that we still have 1 more hour for that, but definitely we're going to take a break. So I think that after this, we're just going to reconvene here in maybe 15 minutes. I think that's an appropriate amount of time. You can get some coffee. You can just, go stretch your leg. And then we're going to start with pen and paper class. That means that I'm just going to be using like a virtual blackboard, and we're just going to start going from there. And the rest of the classes are going to be like that. So before we close it up, I want to ask again, are there any questions? Is there anything that you want to ask, maybe about the scope of the course, how the field is looking at? I'll just open the floor to your questions. All right. If not, Felipe, I think that we can just go into our 15-minute break. I will probably make me a coffee and be around here. If people will just want to discuss during the break, that's also fine. And if not, I'll see everyone at, let's just call it at, for you, it's going to be 12:50. Let's just do 12:15, 18 minutes. So I'll see everyone in 18 minutes. I hope it was a nice break, that you got some coffee or tea or just a bowl of water, whatever you need to get us through the next 40 minutes, which are going to be the first part of the Blackboard, virtual Blackboard, literally for class number 1. So today, in what remains of the first day, what I want to try to do is just quickly go over some of the basic postulates of quantum mechanics that if you've already had a quantum mechanics course, you might know some of this, but it's always good to have a refresher because ultimately, and at the end of the day, that is the basic set of rules that we're going to be using for quantum machine learning. Quantum machine learning is just generalizing the computational model of classical machine learning based on the principles and the framework of quantum mechanics. So being aware and recalling all of the framework of quantum mechanics is going to be extremely important to be able to use the quantum machine learning framework. As usual, if you have any questions, feel free to interrupt me. The notes that I'm going to be working on here, we're going to be sharing them with you, so feel free to note take. But if you're also more like someone that learns through listening, you're still going to be able to access the notes online. I will try to do my best to have like a clear handwriting. I'm not known for having the best handwriting, so if there's anything that is not clear, if you see anything that you can interrupt me and say like, oh, I don't understand what you just wrote right there, just please feel free to interrupt. I will definitely try to do my best to have some clean notes. So let's go to the beginning. Quantum machine learning. Let's talk about quantum mechanics. So historically, we all know that quantum mechanics was developed at the beginning of the 19th century out of the realization that there was a series of experiments whose results and whose interpretation could not be given by classical mechanics. For instance, in 1901, there was the black body radiation. Oh, my pen is actually not working too good, and I tried it. Okay, black body radiation problem that could not be explained by the laws of classical electromagnetism. In 1927, you had this is definitely not, there it is. We had the double slit experiment. And all of these experiments had in common that they needed a new theoretical framework for physics that went beyond the laws of classical mechanics and classical electromagnetism. So we know that Planck's law was developed that quantized the oscillations of a harmonic oscillator. Then in 1905, Einstein was the first person to propose the quantization of the electric field, right? And based on some of those discoveries, the first quantum revolution started, right? This is EM, electromagnetism. And after this, there was a series of further developments that cemented the basics of quantum mechanics. And basically, what we want to try to do right now is review what are the basic rules of quantum mechanics, or what we call the postulates of quantum mechanics. These are a series of mathematical postulates that are going to tell us how to understand, describe, study, and get information out of quantum systems, right? So it is a series of, I believe, 4 postulates of quantum mechanics, and we'll just review them very briefly. And I'm going to try to give a modern interpretation of quantum mechanics, because for people that have done, your classical course in quantum mechanics, teachers in university usually take an approach where you review quantum mechanics the way that it was developed. So you solve like the particle in a well, and you get what's the distribution of the probability of where that particle is going to be in a well. You look at the tunnel effect and whatnot. And while those are extremely important phenomena that are going to be useful to understanding the laws of quantum mechanics and how particles interact with potentials and fields around them, those are not exactly the formalism that we're going to be interested in. For us, quantum mechanics is mainly going to be about analyzing systems of qubits. So most of what I'm going to be trying to say here are going to be the rules just slightly tweaked or just phrased in terms so that we can use them later to understand systems of multiple qubits, right? So let's begin with the first postulate of quantum mechanics, which is about the state vector. So the first postulate of quantum mechanics tells us that associated with any isolated physical system, is a complex vector space with an inner product. This seems again like your basic run-of-the-mill quantum machine learning code, and this is what we call, of course, the Hilbert space. And the state is known as the state vector, known as the state space of the system. And as we just said, the system is completely described by the state vector. So we know the state space, state vector, Hilbert space, I'm going to try to say, which is going to be the relevant information. So essentially what we know is that the Hilbert space is just essentially going to be a complex vector space. We're going to denote the Hilbert space throughout these lectures with the curly H, and we're going to be denoting the state vector already using the Dirac's notation as a ket psi. And what we know is that this is usually going to be a complex vector space of dimension d, and this is just d times 1 complex vector with a norm equal to 1. So we know this is usually expressed like this, that the inner product of this vector with itself has to be equal to 1, and the normalization guarantees that probabilities are preserved. So again, at this point, I'm just giving a very basic overview of quantum mechanics. So then we're going to have our postulate 2. That is about the evolution of quantum states. This tells us that the evolution of a closed system and here closed is going to be important, is described by a unitary transformation. So that tells us that if we have a state psi at time t, a state psi prime at time t prime, with t prime larger than t, then the state of the system was obtained through applying some unitary that depends on t prime t to my state psi, right? And what we know is that we can think about the next part of this corollary, which is about the Schrodinger's equation. Which tells us that time evolution of the state of a closed quantum system is described by Schrodinger's equation. Schrodinger's equation. And Schrodinger's equation tells us that the partial derivative for state with respect to time is equal to h psi, and where h is the Hamiltonian of the system, which, as we've already said previously, it describes the interactions of different constituents of the system. So just brief couple of comments here. So we know that the evolution of this unitary, the unitary evolution of the system, we can always think about it as applying a unitary operator right here, right? And what is a unitary operator? So we know that u of t prime t times u dagger of t is equal to the identity. This is by definition of a unitary operator. What does it mean for here? We're talking about Hermitian. So Hermitian means that it's complex and symmetric, and that means that all of its eigenvalues are going to be real. So that means that H is Hermitian. It means that for any vector x, the expectation value of x, h, x is real. So up to this point, I'm using already some vocabulary, and I'm writing inner products as this notation of bra operator ket. I am already writing this this notation right here, where I'm multiplying a ket by an operator. I just want to ask very briefly for people that are in the course, is this notation something that you're familiar with? Would you want me to further explain what this notation means? I'm just feel free to let me know if this is something that you're familiar with.
Yes.
All right. Okay, I see that people are writing in chat that they're familiar with the direct notation, which is great. If people are not familiar with this, we can just go over some of it. But essentially, this is the notation that we're going to be using throughout the course. All right. Let's keep moving forward. Let's talk about postulate number 3. And again, before going to postulate number 3, we know that if our Hamiltonian is, if h is independent of time, that means that it's a time independent of t, then the solution to the Schrodinger's equation is given by a unitary u of t equals to e of minus I t h, where again h is the Hamiltonian of the system, and this is how the unitary evolution arises from this equation right here. So if we replace this in here, we can see that this solves Schrodinger's equation. I think that's for the remainder of this course, we're just going to be working with time-independent Hamiltonians. As we're going to see, this is a very general case that allows us to do quite a significant amount of things. So for now, for us, let's just quickly go back and say what it is that I want you to keep in mind out of those postulates. Postulate number 1, I want you to know that states are just vectors in a complex vector space. That's the most important thing that I want you to know. Postulate number 2, the evolution of a quantum system is given by a unitary that is usually going to be of this form. So these are going to be the basics that we're going to be using whenever we're going to be talking about quantum computing. So now let's go to the more interesting one, the postulate about quantum measurements and how we can extract information out of a quantum state. So we know that quantum measurements, this might be the longest one text-wise, are described by a collection, let's call it M, of measurement operators. So these are operators that are going to be acting on the quantum system that we're going to be measuring. The index M refers to the measurement outcome. That might occur in the experiment, right? So we know that if initially the state of the system was psi, then immediately after measurement, the probability that outcome X, that outcome M occurs is P of M of the inner product of psi, M dagger, M psi. And the state of the system post-measurement given that we got result M is going to be by this state divided, of course, so that we can renormalize it by the probability of M, by the square root of the probability of M. So again, what do we know about those operators M of M? Well, the operators M of M satisfy the condition that the summation of M dagger M is equal to the identity. And this is what we call completeness. Why is this true? Why does this have to happen? Well, because we know that after a measurement, if we're running with a complete set of measurements, again, like complete that satisfies this property, we know that we need to get some outcome, right? We have a quantum state, we measure some outcome has to happen. And all of the probabilities of all of those outcomes, they need to add to 1. So this means that if we add up together all of those probabilities of all of those different outcomes, we need to get 1. And here, if we just re-expand using the equation from above, sorry, we have this right here. You know, we can always take the summation, put it inside of the inner product. So we have this. And completeness tells us that this right here is equal to the identity. So this is just the expectation value of psi with the identity psi. And this again is equal to 1 because our state is normalized. So the completeness relationship just tells us that the probabilities have to sum up to 1. And throughout the rest of this work, you know, there's general types of measurements, but we will only be concerned with projective measurements. So a special type of measurements that we will consider are projective measurements. So these are described by an observable. And this is what the type of measurements that we're going to be caring for, because whenever we measure a quantum system, we're going to be trying to get the expectation value of some observable. And again, an observable is just a Hermitian operator M that acts on the state space and is going to have some decomposition as summation of M of some eigenvalues M and projective operators Pm. And what these have is that Pm times Pm dagger is equal to Pm dagger Pm and is equal to Pm. And this is what it means to be projective. And more generally, we're also going to assume that they are going to be orthogonal. So that means that if we have something where here we have prime, then this is going to be delta M prime. Let me try to move this so that it actually fits. So we're going to be considering projective orthogonal measurements. And what's really nice about this sort of measurements is that, let's say that we want to get the expectation value of some observable, right? So we want to get the expectation value E of M. Well, then we can do this very simply by just averaging the results of those projective measurements. We just do a summation of M of P of M multiplied by M. So we measure a bunch of times, we get outcome M's, and we just check what's the probability of each one of those measurement outcomes. And of course, just replacing what we previously have, this is M, and here we have psi, Pm psi. This is nothing more than the expectation value of my observer. So computing this sort of expectation values can be easily done by sampling over the states, right? So what is it that I want to try to convey to people out of postulate number 3, postulate about quantum mechanics, is that we already know how to describe quantum states, how they evolve via unitaries, and how do we extract information? Well, we're going to be considering projective measurements. And with a projective measurement, what we're going to have again is take an observable, M, and we're just going to measure in its spaces, in its eigen decomposition. Usually, and this is going to be for quantum computing, usually when we measure in quantum computing, and from now on, I'm going to be using the acronym QC for quantum computing. We measure in the eigenbasis for instance, in a single qubit of the Z operator. So that means that Z has eigenvalues 0 and 1. So we already know that I can express Z. And this, let me know if this is an equation that is obvious to you. But we said here that we can express our operator as a summation of eigenvalues times the projector into that eigenvector. So Z is a 2 times 2 matrix. We can write it like this. And you can see that this can be written as 1 times the projector onto Z, which is the eigenvector associated with the 1 eigenvalue, minus 1 times the projector associated with the minus 1, or with the 1 eigenvector, sorry. So in this case, what we're going to be doing is we have a qubit, and we measure, and we're going to get results 0 or 1. And the probabilities of 0 and 1 are just going to be given by projecting onto those two states. I'm going to get into a little bit more details about this, but this is just to say why those postulates of quantum mechanics are going to be useful. So far, we have those 3 postulates: description of a quantum state, evolution, and measurement. And you can already see why we care about those, because whenever we're talking about variational quantum algorithms and quantum mechanics, this is exactly this is exactly the framework that we use. We have a quantum system, we need a way to describe it, we need a way to evolve it, and we need a way to measure it. So thus far, this is what we have. Then, of course, let's keep going to postulate number 4, which is about composite systems. So how do we describe quantum systems of multiple components? So we know that the state space of a composite quantum system is the tensor product of the state space of the component physical systems. So that means that if I have an n-qubit system, then I know that for each qubit, I have a Hilbert space H that is going to be a two-dimensional complex vector space, right? And then the Hilbert space of the whole qubit system, let's call this Hi, this is for the ith qubit, then the Hilbert space for the whole system is simply going to be described by a Hilbert space which is obtained as a tensor product when I goes to 1 of n, which each one of those Hilbert spaces, and because they're all the same, each qubit is essentially just a two-dimensional, is described with a two-dimensional complex vector space. We usually just write this as n. So let me just call this like this, the state of a single qubit, right? And then we know that we can start describing and we can form a basis of this tensor product vector state by forming a base by the basis of the individual system. So if I have a basis psi I for the ith qubit, then I can write a basis for my whole quantum system by just taking the tensor product of the elements in the basis of all of those constituents. Now, of course, this is just a basis for that Hilbert space. And we know that the states that describe the composite and qubit system are more general than those that live here. This is just a special type of system. And let me just give a specific example. And this is the example that we had in our previous talk. If we have a single qubit, I know that my basis is 0 and 1. If I have two qubits, I can just take the tensor product and do 0, tensor 0, 0, tensor 1, 1, tensor 0, 1, tensor 1, or we usually just write this as 0, 0, 0, 1, 1, 0, and 1, 1. And what we're saying is that the elements of this basis are a tensor product. But those are not the more general states in my quantum system. My more general types of states are going to be states that can be expressed as a summation of tensor product states. Because states of this form can contain quantum correlations, such as entanglement. And those quantum correlations are not expressed in this type of states, which we call separable states. So up to this point, we know how to describe and evolve and measure. And now we're just assuming that this is a multi-qubit state. So this is what this postulates, multi-qubits. Is allowing us to do. So a lot of times, and during my talk, you might have seen that something that I usually use is I use density matrix formalism. Now, the density matrix formalism is a way to also express the states in quantum mechanics, where instead of describing a quantum state by a vector, like we do here, this is a d times 1 complex vector in a complex vector state, we can also describe quantum systems with quantum operators. And this is actually it's completely equivalent to just using state vectors. But as we're going to see later, we can reformulate quantum mechanics in the density matrix formalism. And this actually allows us to describe phenomenon that the state vector representation doesn't allow us to do. So the next thing that we need to do is just rephrase, and this might be perhaps newer for people that have just had basic quantum mechanics course and not modern quantum mechanics course, is we want to rephrase postulates in quantum mechanics in terms of the density operator. Because as we will see throughout this course, this is going to save us a lot of trouble, and it's going to allow us to describe phenomena like interactions with the environment, describe like the subsystems of composite quantum systems. So in this equivalent formulation of the density operator, what we're going to do is think about how the postulates will change. So a density operator allows us to describe quantum systems, just like we said before, described by quantum states, where we know everything about our quantum states. But they're also more general because they allow us to describe quantum systems where we only have partial information about our quantum states, or where the full information is not known. So here we can think about a case, for instance, where we have a quantum state, but instead of being in just a state psi, it's actually in a state psi with a given probability, right? Maybe we have a source that instead of preparing a quantum state every time perfectly, is preparing quantum states, different quantum state psi's with the respective probability pi's. And here what we can do is describe the quantum system by a density matrix, which is essentially going to be expressed in this form. And what we know is that the postulates that we previously have are given by those equations. So the description of the system, postulate 1, tells us that quantum systems are now described by a density matrix. We also know about the unitary evolution, that if we have a state rho prime at time t prime, then we can obtain rho prime as taking our state and evolving it via some unitary evolution, and our evolution has to be expressed in this way. Then we can think also about measurements. How do we get measurement outcomes out of a quantum state? Well, then again, we know that the probability of getting result m is going to be given by the trace of m dagger, m rho. If we have a projective measurement, this is going to be given pm rho. And the state of the quantum system immediately after measurement is going to be given by mm rho m dagger divided by the trace of m dagger m rho. So what are the properties of this density matrix operator? So again, it needs to be a normalized state. So properties, so that it preserves probabilities. This means that the trace of rho is going to be equal to 1. We also want the state rho to be positive semi-definite. This means that for all vector x, we know that the inner product is larger or equal than 0. And this is again so that we can preserve probabilities. Then, because again, we said that density operators allow us to describe, or density matrices allow us to describe systems that go beyond what we can describe with pure states. So we can always go back and we can say, right, so this formalism is more general, but also encompasses the state vector. So how does it encompass it? So whenever our states are pure, that means that rho can be expressed as simply the outer product of a state vector. This is when we recover the usual equations that we previously had, where everything is exactly the same. And here, in this case, what we know is that the trace of rho squared is going to be equal to 1, simply because rho squared equals rho. More generally, whenever we have partial information about our states, or where we only have limited knowledge about the state of our system, we're going to be talking about mixed states. And in this case, what we're going to have is that the trace of rho squared is going to be smaller than 1. We can do this smaller, just like a strict inequality if we want to talk about general mixed states. But for now, this is just a general overview of the tools that we're going to be using. So up to this point, and I think that we're nearing the end of our first theoretical class, I think that this could be stopping point. I went a little bit fast with this because I don't want this course to be a course in quantum mechanics. I believe that people here already have some knowledge on this. I just felt that the tools that we're going to be using really require us to have this knowledge about the basic framework of quantum mechanics. And as you will see, we'll keep coming back into those to understand how this allows us to understand quantum computing. So the next class, what we're going to be doing is trying to understand how the rules of quantum mechanics allow us to understand quantum computing. So we're going to start building some intuition from very simple examples about how we can use this very basic, it's just 4 postulates set of rules so that we can actually get information and information processing tasks in a quantum computing, in a quantum computer system. We're going to be mainly talking at the beginning about single qubit states because the qubit, as we said, is the fundamental unit of information for quantum systems. So understanding very well how a single qubit is described is going to be fundamental to understanding systems of multiple qubits. So we are definitely going to spend some time understanding the basics of single qubit states. The first set of theoretical exercises are about single qubit states. And as we will see, once we have that basic framework put together, in tomorrow's class, we're going to be starting, we're also going to be about halfway through that class talking about how to actually create variational algorithms, what are the different ingredients that we need to have for them. And I think that that's going to give us like a nice overview of the first tools that we're going to need for this quantum machine learning course. As I said, it's very principled, it's very theoretical. So the tools that we have here, if you have any questions about any of those, again, I went very fast because I assume that most of you already know sort of the postulates of quantum mechanics, but if you don't, we can just discuss. And yeah, I think that with that, we can just end today's morning session. We'll meet with everyone in the afternoon. Something that we wanted to say is that due to the inconvenience that we had today in the morning with Google Meet, where apparently now there is like a time limit, we were able to get an account that does not have the time limit. So what we will be doing is updating everyone with new links for your calendars. So essentially, and please correct me if I'm wrong, because I haven't been following the discussion in the organization chat, is that the invitations that you have in your email, please disregard those. I believe that you can delete those because we're going to be sending new links that you're going to be using for today's afternoon hands-on session and for tomorrow's lectures. So please disregard the current links, and we're going to be using new links which do not expire and which we'll hopefully be able to use without further interruptions. At this point, again, I open the floor. Are there any questions up to this point?
Nothing. We are okay. Thank you for the information.
Okay, perfect. So we will see everyone. I believe, let me check my calendar. When is the next? Oh, I just was not supposed to go here. Just in an hour. I believe we have 1 hour for lunch, and I don't want to take more of your time. So I'll see everyone in an hour. Take care.
Okay, thank you.
Thank you. See you soon. Bye.